Good morning. It is morning here as I'm recording this, but the nice part is I didn't have to dress out for work as I'm recording this, which be thankful that you can only see my screen. That's all I have to say. So when you're taking this class, I will be in DC in the on Capitol Hill talking to senators about the Treat and Reduce Obesity Act, which is a piece of legislation to advocate on the behalf of the obese. So, and I was really pressured to go, and this is probably the last year I can do it. Anyways, let's go to something more interesting, which is topological conjugacy. So where everything is going, you did this work now with maps over symbol spaces, the symbol space. I'm not going to go back to those last problems that we did. Maybe we'll go back to some of those and revisit. I kind of want to move on, especially because of the comments that you uniformly made that you don't see where this is coming together. I want to get to where this is coming together as quickly as possible. So where we're going is we're going to a concept of topological conjugacy. So it's again this idea of taking one world and then mapping it to another world and relating the two. So we're going to relate the shift map to the logistic map, which we played around with quite a bit at the beginning of the term, but only for larger values of r, where r is bigger than 4, because that's where it gets interesting. If you recall, you can just go back and scroll your parameter in that one Excel spreadsheet that we made, where you can see that when r gets bigger than 3, 4, you start to get some interesting things. What you get there, if you recall, were trajectories that did not look periodic. They did not look like they were converging to a fixed point, but they did not look like they were diverging to infinity or minus infinity either. They looked like they were just bouncing around somewhere without a pattern. What we're going to do is, it's really hard to prove these things for the logistic map, so we're going to prove them for the shift map, and then we're going to relate the shift map back to those points under the set of points under which, when we iterate the logistic map, they actually don't diverge to minus infinity. It turns out that that set of points where their initial conditions and they don't diverge away turns out to be something we've seen before. And that's what today's class is about. So get ready, buckle up, it's going to be wild. Remember the Cantor Set? The Cantor Set is what I started out with in the term, and it was this set where you took the unit interval and you plucked out the middle third. You were left with two little sticks. You plucked out their middle thirds. So for each little stick, you kept plucking thirds, and you did this forever. And we talked a little bit about what happens if you do this forever. It's called, some people call it Cantor dust. It's an uncountable set. So it's got stuff in there, it's not empty, but it also has something called measure zero. So it has all these weird properties. So just keep that in the back of your head. Just remember that we did that. So we're going to look at the logistic map for r bigger than 4. So what I would like you to do is upload pictures of your work as emails or texts as we go through, because I want this to be interactive so they can see things. And you can just upload them right from class itself. And then I get a feel for how much was done when it was done. So I don't think you're going to get through all these modules. So what I'd like you to do is, maybe as a class, maybe someone decide who's going to send me a text and let me know where you ended up. The first thing I'd like you to do is take that fr of x and find the maximum value of that parabola. Use calculus to find it. Check with your classmates to make sure that you found the same thing. So I want the x and y coordinates, and you can just send me the x is equal to and the y is equal to. Right? So that's module 1. Just go for it, and I'm going to pause my voice.